Namaste bachcho, welcome back to Rama Teaches You. Today we are going to start the third video on the IB chapter, electric field and magnetic fields. Okay, in the previous two chapters we have already discussed what are charges, what are like charges, what is the Coulomb's force, okay, Coulomb's law, and then we discussed the electrical fields. Electric field is what? Electric field is the force experienced by a charge at a certain distance from that charge. Okay, so basically it is the force per unit charge. Force per unit charge is electric field. Now in this class what we are supposed to do is basically learn the electric field lines. How does electric field lines originate? How do they look like, and what effect do they show on the charge? Okay, let's go. Electric field lines show the direction of force acting on a test charge and helps us to visualize the shapes of electric fields that arise from the static charge. The field lines are imaginary, but they give us a clear impression of the variation of field strength in the spaces between the charged plates around a point and the charged spheres and other arrangements. So, why do we have field lines in the first place? Do they actually exist? No, there is no actual line that is coming out of that what do you say, out of that charge. But for us, we have always been visual learners. Okay, if we try to visualize something we learn better. So to understand how the strength of the charge is going to be when it is going across, how the strength of charge is going to vary as we move away from the charge or towards the charge, we want to visually understand it. And that visual understanding is helped by understanding how the electric field lines actually work. Okay, the concept of field lines was first introduced by our famous hero, Michael Faraday, right? Michael Faraday is the hero who started the whole electrical, like I basically feel that most of the laws that we see are somehow originated either directly by Faraday or by using Faraday's laws. Understood? Now, his original idea was a set of elastic tubes that repelled other tubes rather than a set of lines. Okay, so he considered them to be small tubes. These are some conventions for drawing these field lines. The lines start and end on charges of opposite sign. It starts from one end and ends at the other. They do not form a closed loop. Okay, that closed loop is not there. They originate from the positive charge and they terminate in the negative charge. Okay, the arrow is essential to show the direction in which a positive charge would move, that is, away from the positive charge and towards the negative charge. So, whenever you are drawing field lines, always remember to mark the arrows. Where the field lines is strong, the lines are close together. The lines act to repel each other. So basically, it's like this. If you have a positive charge here, there is plus q charge. All the field lines would be coming out like this. Okay, all the field lines would be coming out like this, straight out of this charge, right? Now, what do you observe? When you are closer to the charge, the field lines are also very close to each other, right? When you are closer to the charge, the field lines are also very close to each other. But as you move away from the charge, there is so much gap between the field lines, right? So when you're close, it's like a bicycle spoke, right? If you have ever ridden a bicycle, you would have observed that all the lines that are in the tires, okay, they all originate from the middle and they terminate at the rim, right? So we can see that it is easy for us to place our fingers at the end tire end portion. But if we try to do the same near the axle, what happens? It is not possible because all the sticks are so close to each other. That is actually how we can visualize the electric field lines coming out of a positive charge. The lines never cross each other. Okay, why don't the lines cross each other? Because the electric field lines have a responsibility to show the direction of force that a particle would experience if placed at that point. Okay, you cannot have two directions of force from at a single point. That's not possible. One charge cannot influence another charge in this direction and in this direction at a particular point. It will only be able to influence it in one direction. So in order for that to happen, these field lines should not intersect with each other. I can show you a visual representation. For example, if you have a charge like this and if you have another charge like this, okay, the charges like this will not happen at all. But if you have a charge, no, I'll actually make it more sensible. Okay, so imagine you have a field like this and a field like this. Okay, now at the point of their intersection, at the point of their intersection, this particle is going to have a direction in this way as well as in this way, and that cannot happen by a single charge alone. It cannot. You cannot have two directions at a particular point, okay, by a single charge. Though the lines meet and meet a conductor surface at 90 degrees. What does that mean? So basically, even if a field line is going like this, if there is a surface here, it will always be 90 degrees. Okay, it will always touch the surface at 90 degrees. However, the angle may be, it will always touch and go into the conductor at a 90-degree angle. Understood? So basically, the field lines are perpendicular to the surface of the conductor. Next, the radial. Okay, is this important? No, not required, not really. Okay, this is something that we you have already must have done in ninth class and 10th class. Now, the radial field due to a point charge. The electrical field lines radiate outwards from a positive point charge and inwards towards a negative point charge. So, if you look at this, the blue colored dot is the positive charge and the orange colored dot is the negative charge, and we can see that from this blue color positive charge the field lines are going outwards, right, and onto this negative charge the field lines are terminating or going inwards. This is true for all positive and negative charges. Understood? They originate, the field lines originate from the positive charge and terminate at the negative charge. Okay, so as with the similar pattern in gravitational field, the this is also a radial field. Okay, even gravity, mass also has a field like this only. If you have a mass m, the gravitational field lines will look exactly like this. Okay, like the spokes of a wheel or the radial path. They will also follow a radial path. Clear? The field between 2 point charges. It is not hard to imagine how the two separated fields of figure 12 combine to give the case where the point charges are closed. There are two cases possible, like two like charges and two unlike charges. Although a 2D view is given, the field are of course in three dimensions. Okay, so basically it's like think imagine this as a football. Inside the football you have placed a small charge, and basically the charge is producing field lines which are perpendicular to the surface of the football. Okay, it is going in all directions, just as the ray of the sun. The sun is projecting light in all directions, right, not just towards one direction, right, not just towards us. It is basically illuminating the whole sky 360 degrees. Similarly, the charge is also producing field lines exactly like that as a sphere. That is why we call it a radial design. We call it a radial design because in a 3D space it is forming a sphere. Okay, next, let's go. So, like charges. Now, there will be a point where the field is zero, somewhere between the charges, where the electric forces on a test charge are equal and opposite. See, Akshay, what is happening here? This field is also producing positive field lines. This charge is also producing positive field lines. I'm sorry, this charge is both these charges are producing positive field lines that are going outwards. Now, what happens due to these two? These two field lines do not want to come close to each other. They want to repel each other. And that is the reason why two charges repel each other. One's field is not ready to interact with the other field. Both of them want to create their own space. Therefore, what happens? This charge exerts a force on this charge, and this charge exerts a force on this charge. And what do you observe? You observe that there is a repulsion. Now, what happens when we have unlike charges? As we know, unlike charges are basically a positive and a negative charge pair, right? A positive and a negative charge pair. So what happens? The electric field lines now link the two unlike charges in the direction that is from positive to negative. Again, the electric field lines originate from the positive direction and they terminate towards the negative direction. This is there is some resemblance to the field lines produced by a bar magnet that you will see later in this topic. When we study the magnetic field lines, we will come across the same field lines pattern when we have two north poles together. Okay, and we will have this same field line like this when we have a north pole and a south pole together. What is happening here? All the positive field lines are getting originated from the positive charge, and all of them are going towards or entering the negative charge. Okay, so what do you observe here? There is no electric field which is zero between these two charges. Between these two charges there is attraction. So the field between two charges with unlike nature, that is a positive and a negative charge, will never have an empty field. But between two positive charges or two negative charges, you can have an area where the electric field will be zero. Understood? So unlike charges, the field will be zero somewhere in the middle. Okay, next, the field between two parallel charged plates. Okay, two parallel charged plates. Now, what is a plate? A plate is a thin rectangular surface, okay, on which the charge is spread across. Okay, it's a metal plate where in which the charge is spread across. An electric field exists in a space between two identical metal plates that are connected to a DC power. A positive plate charge in the electric field is attracted to the negative plate and repelled by a positive plate. The field patterns are shown as follows. Now, when the field lines are inside, when the field lines are inside the two plates, inside the edges, inside the edges of the two plates, what do you get? You get a parallel field line, a parallel field line between these two plates. But when you are very close to the edge, the field lines, they are like wires under tension. Okay, if both the wires are stretched like this, hold on, I'll explain this to you a little bit better. One second. So guys, can you see this stick? So this is what, this is a field line. Okay, so this is a field line. Now, when the electric field line is inside the edges of the field, basically they are under tension. There is a very short path, so they will remain straight. Okay, they will remain straight. But as soon as they move towards the edge, what happens? They have a leeway, due to which what happens? The field lines, because there is an extra space possible, the field lines will start bulging outwards. They will start bulging outwards. Understood? I hope this is clear. You can see the stick. So inside, because there is no distance, all the sticks are cramped together. They are all cramped together. All the field lines are straight. But once you have a little bit of a leeway, when you reach the edge, what happens? The stick bends. The field lines bend. They move outwards. Understood? Okay, let's move on. So, okay, now the field. Now, if you have electric field lines that are parallel to each other and close by, if you have parallel field lines, okay, which are close by and uniform, you get a uniform field line inside the plates. Okay, inside the edges, because all the field lines are parallel to each other, you will get what? You will get a uniform electric field. The field becomes zero at the edges. This is known as the edge effect. Okay, what I showed you right now, it is the edge effect. This is where the field changes from strength inside the plate to a value outside the plate, often zero. You should be able to use the property of the field lines to explain that there cannot be an abrupt change in the field strength. At the plate edges, the field lines curve outwards as the field gradually weakens from a large value between the plates to a much weaker value when you go away from the plates. Now, this is not possible. Why do we have the edge effect in the first place? We have the edge effect because you cannot, basically, the gravity cannot suddenly become zero. The electric field cannot suddenly become zero. Like basically, when you were inside the plate, you were under the effects of the electric field. But as soon as you move out to outside the plate, it's not like you're not going to experience the field of the plates. You will experience a decrease in the field strength. You will experience a decrease in the field strength again due to what? Because if the field lines are not concentrated in a particular region and they are allowed to spread out, the electric field weakens. So what happened? When the electric field lines were between the edges, they were close to each other. But as soon as the edge as soon as the edge arrived, what happens? The field lines started to spread out. They started to spread out, and it will actually look something like this. See, so the field lines are spreading out, and once you have spread out field lines, what happens? The electric field strength drops dramatically. It will stop, it will drop drastically. Clear? Just give me 1 second. Uh, okay. So the field lines will become zero when you cross the edges. Next, so at the plate edges, the field lines curve outwards as the field gradually weakens from the large value between the plates to a much weaker value away from the field lines. For the purpose of this course, you should assume that the curve begins at the edges of the plate. Okay, it begins a little away in the edges. Actually speaking, what happens inside the edges itself, the field basically starts to decrease when you are about to go to the edges itself. Like look at here, see, basically here itself it will start to curve, but we are not going to focus much on that. We are only going to assume that the field will start curving after the edge is coming, after we cross the edge. Okay, next. Sometimes field lines are called lines of forces. These lines represent the force acting on a positive test charge, by definition, with direction indicated by the arrow on the field line. When the line is curved, the tangent at that point on the line of force gives the direction of the electric field line. What does it mean? If you have an electric field line like this, at this particular point, if you want to understand what the direction of the field at this point is going to be, it will be a tangent like this. At this point, it will be a tangent like this. At this point, it will be a tangent like this. So if you have a curved field line, at any point on that curve, if you draw a tangent, you will get the direction of the electric field at that point. Clear? Any doubts? Mute பண்ணிருக்காரு. Oh, yeah. Okay. So, oh, okay. So, yeah, when the field line is curved, the tangent is that point on that line. Force gives the direction of the electric field acting on that positive charge. The relative density of the line, how close they are, indicates the strength of the force. Next topic. Imagine that you are a small test charge sitting in the middle of two horizontally uniform and oppositely charged plates. You can see that the plate stretching out of the distance in the horizon, how much as if you were standing in a huge flat field, except that there is also a plate overhead. The view would be the same in all horizontal directions, and so the electric field must be vertical. Imagine moving to the side a short distance. Since the plates are uniformly charged, your view would hardly change. As a result, the electric field due to the plates will be the same at the new position. The field must be uniform. What are they trying to tell you? Imagine you are inside, there is a plate underneath you, there is a plate above you, there is a positive charge plate above you, there is a negative charge plate below you. So basically, just as if rain would fall on you. Okay, when rain falls, there is the same amount of drop of water coming here also and here also. That's what you have to imagine. Now imagine that you are standing between two plates, and the electric field is just pouring over you. The electric field is just pouring over you. Now if you move a little bit here, you will get the same amount of electric field lines pouring over you. If you move a little bit here, what happens? Again, the same amount of electric field lines is going through you, is pouring over you, right? So what does this tell you? This tells you that between two plates, you will always get what? You will get, or you will always get a uniform electric field. Okay, I'm not talking about the edges. I'm not talking about the edges. It should be the if you are in the middle, if you are in the middle area of the plates, then you will get a uniform electric field. I hope this is clear. Now imagine that you're moving to the edge of the plate. If you are centrally between the plates, then any horizontal contribution to the field from the positive plate will be cancelled out by the opposite contribution to the negative plate. This would not be true if you were not positioned at equal distances from each other. Now, through the plates, though the plate will only occupy half of your field of view, the electric field strength is half the strength it was at the center. Now again, I want you to imagine you are moving towards that part of your city where the rain is slowly decreasing, right? What happens if you're a traveler? You must have observed that when you're driving a car, it is sunny, shining, and basically as suddenly what happens, you enter the area where it is raining. What happens? The sky becomes darker, and you start to feel more and more water pouring. Once you go into the center of into the center of the rain cloud, you feel the maximum amount of water that is pouring through you. The same can be done said about this also, right? The same can be explained here also. Understood? This is how you have to imagine the electric field lines between two plates. Understood? As if you are walking in a field with the clouds above you pouring on the rain and the ground beneath you. Okay, both of these are plates. Understood? Next. So, again, I'm going to skip the experiment. Okay, and I'm going to go straight on the potential difference between parallel plates. The uniform electric field The uniform electric field between two charged plates provides us with another way to think about electric field strength. In figure 17, a positive charge with a size q is in a field between two charged plates separated by a distance d, right? There is one positively charged plate here, one negatively charged plate here. Both of them are separated by a distance d. The field has a strength E. The force acting on the charge is what? Force is equal to the force per unit charge multiplied by charge, that is electric field multiplied by charge. So force is equal to electric field multiplied by charge. Work must be done on the charge to move it towards the positive plate at a constant speed. This is force times distance moved in the usual way. The field lines are parallel to the displacement, so there is no component of force to worry about. The force is zero because what is happening here? The direction and the application of force are at an angle of 90 degrees, so you don't have to worry about the force, the basically the force. Okay, so all you are doing is doing some work. Okay, to bring a unit positive charge small q from this negative plate to this positive plate. Okay, how much work do you have to do? For example, Akshay, the field lines are originating from the positive charge and they are terminating in the negative charge. Similarly, the electric field is what? The gravitational field is what? It is originating from the earth and it is moving towards space. Now, Akshay, when do you as the observer has to do work? If when you're falling towards the earth or when you're jumping away from the earth, when you're jumping away from the earth. So basically, when you move away from the earth, when you move in the direction opposite to that of the electric field, you have to do work. A positive charge has to do work because it is going towards the positive plate. There is a repulsion there. When I pick up a pen and I slowly bring it upwards, I have to do work. I don't have to do any work when I am dropping the pen. Right? I don't have to do any work when I'm dropping the pen. But when I'm lifting the pen, it's a whole different story. I have to apply the amount of work. Okay, so the work done is equal to force. The force that is acting on the charge. Okay, force times charge multiplied by distance. Right? That is the electric field. Sorry, the force times distance or the electric field times charge times distance, where x is the distance moved. When the charge is moved from the negative plate to the positive plate, the work done on the charge is what? EQD. So basically, Akshay, you were doing what was the force with which you were moving the charge from here to here? Force is equal to electric field multiplied by charge, and you moved it a distance of d. So work done will be equal to force times d is equal to electric field multiplied by charge multiplied by d is equal to EQD, right? EQD. Understood? So the potential difference V between the work done between them is EQD. Now from topic B5, the potential difference V between the plate is what? In B5 we have learned that potential difference is what? Work done upon charge. Potential difference is defined as work done upon charge. Work done in moving a charge upon the magnitude of charge. So potential will become equal to what? E Q D upon Q is equal to ED. Okay, so this is how you get the formula that potential is equal to field times distance. Potential is equal to field times distance, or electric field is equal to potential upon distance. Understood? Okay, fine. Shall we move on? Okay. So, the electric field strength can be written and calculated in two ways. Force acting on a charge upon magnitude of charge. That implies that the unit of electric field is what? Newtons per coulomb. Potential difference upon distance moved. That is also electric field. So that implies that the unit of electric field strength is volt per meter. So you can either have newtons per coulomb or volt per meter. These give two alternative units for electric field strength as well as two ways to calculate them. Okay, force upon charge, Newton per coulomb. Potential upon distance, that is volt per meter. To see this, write Newton per coulomb, kilogram meters per second square per coulomb, kilogram meter square per second square upon coulomb meter is equal to kilogram meter square second square upon coulomb multiplied by 1 upon m. You will get volt upon meter. Understood? These are the same equation. These both of them are similar. Newtons per coulomb and volt per meter, both of them share the same dimensions. You know what dimensions are, right? Length, mass, basically the fundamental units. You have the seven fundamental units. You have the length, you have the mass, you have the time, you have the number of moles, you have the temperature in Kelvin, you have luminosity, and different, exactly. So these are the seven fundamental properties. Writing the equation in full form, the uniform electric field is given as what? Between two plates is given as electric field is equal to force upon charge is equal to volt upon distance. In practice, it is easier to measure a potential difference with a voltmeter in a laboratory than to measure a force. So an electric field strength is usually expressed in volt per meter, because you can always find the field, you can always find the potential. Just place a voltmeter, one terminal on the positive and the other on the negative, and automatically what will you get? You will get the potential across these two plates. You will get the potential across these two plates. So it is easier to measure the electric field with the potential upon distance formula. Understood? So commonly electric field is expressed in volt per meter. Understood? Okay, a pair of parallel plates with a potential difference between them of 5 kilowatts are separated by a distance of 120 millimeters, or we can say 0.12 meters. Calculate the electric field strength between the plates. What is the electric field strength going to be? We know that electric field is equal to volt upon distance is equal to 5 into 10 to the power of 3, that is 5 kilovolt upon the distance between them is 0.11, or I will just simply write it as 12 into 120 into 10 to the power of minus 3. So if I take this minus 3 up, I will get 5 into 10 to the power of 6 upon 120. I can write this as 5 into 10 to the power of 5 upon 12. Now, if you divide this, you will get 4.2. 4.2 into 10 to the power of 4 volt per meter. Understood? Okay. The electric force acting on a doubly ionized oxygen ion between the two plates. Doubly ionized oxygen ion is what? Doubly ionized oxygen ion. Ionized means you removed the electron. Ionized means you remove the electron. So what do you get? You basically, they are asking about O2 plus. So basically, how much charge will it have? One oxygen ion will have 2 units of positive charge. So basically, 2 electron, 2 multiplied by a charge of the electron will be the overall charge in this. Yeah. So can I write the charge, total charge on the is equal to 2 multiplied by E is equal to 2 multiplied by 19 is equal to 3.2 into 10 to the power minus 19 coulombs of positive charge. Okay. Now, the basically we also know that force is equal to force per unit charge, that is the electric field, multiplied by the charge. So force will applied will be how much? We found the force to be 4.2 into 10 raised power 4 volt per meter is equal to 4.2 into 10 to the power of 4 volt per meter multiplied by the charge, which is 3.2 into 10 to the power of minus 19. Understood? This is the force that is being applied on the oxygen ion. Okay, so what are the formulas that you need to remember? The three formulas that you can remember for now is force is equal to K Q1 Q2 upon R square. Electric field is equal to K Q upon R square, or you can say electric field is equal to force upon charge. Okay, and then you have electric field is equal to your force upon charge is already there, volt upon distance. Okay, So remember these formulas. Clear? Okay, next. Pair of parallel plates are separated by 80 millimeters. A droplet with a charge of 11.2 into 10 raised to power minus 19 coulombs is in the field. Calculate the potential difference required to produce a force of 3.6 into 10 raised to power minus 14 newtons on the droplet. Okay, very interesting question. What have they given us? They have given us the value of D. Okay, they have given us the value of charge Q. Okay, and they have given us the force is also given. Okay, charge is also given, distance is also given. Now calculate the potential difference. We have to calculate the value of V. Okay, these are all the things that we know. Can I use force and charge to produce the field? See, electric field is equal to force upon charge. You found the electric field. Using that electric field, can I find electric field is equal to volt upon distance? Therefore, volt is equal to electric field into distance. You understand the logic? So, from the force, you found the field. From the field, you will find the potential. Understood? Okay, let's move on. There's one more question. The plates are now moved closer to each other with no change to the potential difference. The force on the droplet changes to 1.4 into 10 raised power minus 13 newtons. Calculate the new separation of the plate. Okay, so what happened? The potential did not change, but the force definitely changed. Okay, the potential did not change, but the force changed. So let's see from again from the force. Okay, from the force, can we find the field? Okay, from the force we can find the field. The potential did not change, that is whatever potential we got in the first case is going to be remain the same. Okay, so basically we have the force here. So force multiplied by charge will give us the new electric field. Okay, E dash. Force, this is F dash multiplied by charge is remaining the same, so you get E dash. E dash is equal to this old voltage upon D dash. So therefore D dash is equal to volt upon E dash. Understood? So basically, the only the distance changed. The potential did not change. But since the force changed, the field changed. The force changed, the charge remained the same. So the field had to change. Because the field changed, the distance also changed. Clear? Do I need to solve it now? No, right? You understood the basic logic behind it, right? Huh? Solve it and show it to me. All the questions that I asked you to do yesterday, did you complete them on the previous class? No? Okay. Do it today and show it to me. Okay? So basically, I want you to do exactly what I say. All of these questions that I'm doing in class, you should be able to. Don't look at the answers. Okay? Even if you have solved questions, don't look at the answers. Try to solve them on your own. Understood? Let's move on. Okay. A charged particle of mass 2.5 grams is placed in an electric field between two charged plates. Okay, the mass is given for some reason. The potential difference between the plates is 8 kilowatts. V is given, and the plates are separated by a distance of 12 centimeters. D is given. Calculate the electric field strength between the plates. First things first, we don't need the mass to calculate the electric field strength. So we know that electric field is equal to V upon D. Both V and D are given. Can we calculate the electric field? Yes, we can calculate the electric field. Now, the particle accelerates towards the positively charged plate with an acceleration of 1.6 meters per second square. So basically, your force, downward force, is given as, no, let's see. Um, let us assume that these are the two plates. Okay, the particle accelerates towards the positive charge plate. Are they horizontal plates? the a parallel plate of a charged particle of mass is placed in the electric field between two charged plates. The potential difference between, okay, they haven't given us the orientation of the plates. That is fine. So the particle accelerates towards the positively charged plate with an acceleration of 1.6 meters per second square. No other force than no other force than the electric force acts on the particle. Oh, okay, fine. Determine the magnitude and the sign of the charge. We can do this. We can do this. We know the force. Okay. We know the mass. We know the acceleration. We know the mass. We know the acceleration. Can we figure out the force? Force is equal to mass times acceleration. We know that force is equal to mass times acceleration. So we know the mass, we know the acceleration, we know the force, right? But we also know that force force is equal to electric field times charge, right? We calculated the electric field in the first question. Okay, now we use this electric field and the value of force to calculate the charge. So charge will be equal to force upon electric field. Understood? Okay. Now, no need to solve this, right? Logic, you if you understood, it is fine, right? So when you are solving this again, I will put thumbnails in your video also. I have not done it yet, but I will put thumbnails in your video. It's not going to take a lot of time. So if you have any doubts, if you when you do these questions again, if you want to understand what the logic I'm using, you can go to that particular question. Understood? Clear? Okay. So please complete them and send it to me. Like I'll give by tomorrow. Actually, before tomorrow's class, I need a PDF. All you have to do is solve the questions in your notebook and show me as a PDF. Okay, that will be my guarantee. Okay, a particle of charge plus 15 nanocoulombs. Okay, we know the charge between two parallel plates separated by a distance of 2 meters, 2 centimeters. We know the value of D. The electric force acting on the particle is, we know the force also. Okay, sorry, why am I? We know the force also. Calculate the electric field strength at the position of the particle. Oh, easy, right? Electric field is equal to force upon charge. Okay, they have given us the force, we know the charge, so basically we can calculate the electric field. Okay, so electric field is equal to force upon charge. Now the potential difference between the plates. Now you know the electric field in the first question. From the first question you know the electric field. This electric field can be used to find the potential. Potential will be equal to what? Electric field upon distance. Sorry. What am I writing? uh, Electric field into distance. Okay, so you knew the charge, you knew the distance, you knew the force. By using the charge and the force, you calculated the electric field. By using this electric field, you were able to calculate the potential. Now, how am I able to do this so easily? Because of practice only. Okay, your mind needs to tell you, okay, all of do you see one thing? In your exams, you always tell me, no, there is one big question and there are like multiple 4 or 5 questions that are all connected to each other. This is a practice of that. Okay, this is a practice of that. Now, okay, electron volt. You have to tell me how to access that website once more. Akshay. I forgot that questions page. No, after class or tomorrow, you let me know how to access that again so that I can take questions from there that I feel are more interesting and solve them in class. Understood? Okay. The electron volt, the energy. Now we have talked about force. We have talked about field. We have talked about potential. Now, finally, we are going to talk about potential energy. Force, field, potential, and finally energy. Okay, this is how the needle goes. Okay, this is how you thread the needle. If you understand the logic of the flow of information, it becomes easier for you to memorize all the formulas. Okay, force, field, potential, now finally energy. Now electron volt, don't confuse with the name. Electron volt is not what it seems. Electron volt is not potential. Even though there is a volt at the end, it's not potential. It is the unit of energy. Electron volt is similar to joules. Okay. Huh? 1 electron volt is equal to 1.6 into 10 raised to the power minus 19 joules. Okay, that's what an electron volt actually is. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. So electron volts and joules have the same dimensions. They represent the same thing, energy. Joules also represents energy. Electron volt also represents energy. Understood? Don't confuse this with potential. Okay. Now, the energy possessed by an individual electron is very small. When a single electron is moved through a potential difference of 15 volts, then a work is done. Right? We know that what is a potential? Work done upon charge. So, therefore, work done is equal to what? Potential into charge. So, you are doing a certain amount of work. The energy gained by this electron is how much? 115 into 1.6 into 10 raised to the power minus 19 joules. Now look at this. Check. This is basically, there's a pen lying here. Okay, there's a pen lying here. Now, when I push my hand upwards, I am doing work. Because I'm doing work, this pen is gaining energy. So if I remove my hand like this, what will happen? The pen will fall towards the ground. Understood? So every single time work is done on a charge, it is storing that work in the form of energy. It is storing that work in the form of energy, which it can use to basically, as soon as the work is done. So for example, Akshay, look at this. You have a positive plate. This is a positively charged particle. Now, when you are bringing this positively charged particle close to the positive plate, what happens? You are doing work. Why are you doing work? You're doing work against this repulsion between this positive plate and this positive charge, right? Now, as soon as you leave this pen, what will happen? The pen will suddenly go in the opposite direction. How does it have the energy to go? Right, it is getting this energy from the potential itself. The potential energy, when you were doing work against the electric field, the charge was storing energy in the form of potential energy. Like it's just the same way as you compress a spring. Whenever you compress an object with the spring, what happens? As soon as you remove the work, as soon as you remove the force, what happens? The object just gets thrown away, right, forward, because of the decompression of the spring. Because of the decompression, you can imagine this to be the same. When work is done against the field, the charge is storing the energy. The charge is storing the energy because if if the force is removed, if the work stops happening, then you have to take this charge from this position to a position far away from you, so that you don't feel the repulsion. Understood? And you cannot simply remove the charge from one place to another, because you need to have energy. Energy is what allows you to do work. Understood? Now if you have a charge like this, one second, where did I throw my pen? Yeah. Okay, so this thing, if you bring this close to this, and if you try to remove your force, if you try to remove your force, the charge should not stay here. The charge should not stay here. Okay, it should go away. It should go away. Now how does it go away? It goes away by with the help of the stored energy that it had. Understood? So I'm giving you a very detailed analysis of what is happening. Okay, you are doing work against the electric field. Because of that, energy is getting stored inside the charge, and as soon as you remove the force, the charge that is stored inside will basically allow the charge to move away a comfortable distance away from this field, so that the repulsion stops. Okay, that is the reason why every single time I try to drop the pen, what happens? Okay, all the potential energy that was stored in the pen gets converted into kinetic energy. Every single time I do this, it gets converted into kinetic energy. Understood? Yeah, because the first question that we are going to do is potential energy converted to kinetic energy only. That is why I'm specifying this example again and again. Okay, an electron initially at rest is accelerated. Oh, sorry, I jumped ahead. Now, this small quantity involves large negative power of 10. It is converted, it is convenient to define a new unit for energy and work done. What is an electron volt? The electron volt is defined as the energy gained by one electron when it moves through a potential difference of 1 volt. That is the actual definition of 1 volt. If you have a charge, if you have a charge of, let's say, basically if you have a charge and you are placing it in an electric field with in an electric field with a potential of 1 volt, what ends up happening? The amount of energy gained by that charge will be equal to 1 electron volt. So what is 1 electron volt? 1 electron volt is equivalent to 1.6 into 10 raised to the power minus 19 joules. The electron volt is used extensively in nuclear and particle physics. Understood? Theme E, which is going to be the last theme of the book. Okay, an electron initially at rest. Worked example number 9. Okay, worked example number 9. An electron initially at rest is accelerated through a potential difference of 180 volts. Calculate for the electron again in the kinetic energy and the final speed. Okay, so what all do we know? We know the charge of the particle because they have specifically mentioned the electron, right? By name they have mentioned it, so we know the charge of the particle. We also know the potential difference. Okay, so what will be the this thing? The energy, charge into potential, right? So the energy gained, the electrostatic potential energy gained by the electron will be equal to 180 multiplied by 1.6 into 10 to the power minus 19. Okay, 180 multiplied by 1.6 into 10 to the power minus 19 is equal to 2.9 into 10 to the power of minus 17 joules. This do you understand? Yeah. Okay. Now, the kinetic energy of the electron is equal to whatever potential energy it had, right? Whatever potential energy it had, everything is going to get converted into kinetic energy. So, basically, potential energy is equal to kinetic energy. So, potential energy was how much? It was equal to 2.9 into 10 raised to the power minus 17 joules. 2.9 multiplied by 10 to the power minus 17 joules is equal to half into mass of an electron multiplied by the velocity of an electron squared. What is the mass of an electron? We know the mass of the electron to be 9.1 into 10 to the power minus 31 kgs. So basically, velocity of the electron square is equal to 2.9 into 10 to the power minus 17 into 2 upon mass of an electron, which is equal to 9.1 into 10 to the power minus 31. So V will become equal to what? Root under 2.9 into 10 to the power minus 17 multiplied by 2 upon 9.1 into 10 to the power minus 31. Once you feed this to the calculator, it will give you the answer. Do you understand the logic? First things first, what did we do? We calculated the potential difference. Sorry, we calculated the potential energy gained. And then we said that whatever potential energy this particle gained is going to be used as kinetic energy for the move outwards. Okay, when the particle is about to move outwards, that is the kinetic energy. Clear? Okay. Now, so V becomes equal to 8 into 10 to the power of 6 meters per second. That's a large velocity. Next, in a nuclear accelerator, a proton is accelerated from rest and gains an energy of 250 mega electron volts. Estimate the final speed of a particle and comment on the result. Okay, so we know that. Actually, look at this. So, electron volt is equal to half mv squared. Okay, so v is equal to 2 ev upon m root. This is the actual formula. Understood? Okay, this is the formula that you have to use here. So again, they are asking us to find the speed. So what will be the value of the speed? You just put that in the equation, 2 multiplied by what is the potential, 250. Oh, we have to convert this. So Akshay, one more thing. Because the speed is in meters per second, because the speed is in meters per second, you have to convert the electron volt into joules first, because joules is a unit that has meters and seconds in the formula. Kilogram meter square per second square. Okay, so you have to convert the electron volt into joules first, and then and only then will you be able to calculate the value. Okay, so what do we know? We know that 250 mega electron volts multiplied by 1.6 into 10 to the power minus 19 will become equal to how much? 4 into 10 to the power of minus 11 joules. So the electron volt was converted into joules first. Okay, now this energy is going to be used here. Okay, this electron volts gets replaced by joules. So this will become equal to V is equal to root under 2 multiplied by the potential energy upon mass. Potential energy, electron volt got converted into potential energy, joules. Okay, then M. M is what? Proton. Proton mass is how much? 1.6 into 10 to the power minus 27 kg. Okay, here they have rounded it up to 1.7. Okay, 1.6 something into 10 to the power minus 27 kg is the answer. Okay, now the numerical answer for B is how much? 2.2 into 10 to the power 8 meters per second. Now 2.2 into 10 to the power 8 meters per second is not a joke, because the fastest thing that moves in the universe, the light, right? It only travels at 3 into 10 to the power 8 meters per second. So this is two very close. Okay, this is a large speed, 70% of the speed of light. In fact, the speed will be less than this, as some of the energy goes into increasing the mass of a proton through relativistic effect. Now, what happens when you go with the speed of light? Your mass increases. Did you know this? The reason why we cannot move with the speed of light is, if we try to move with the speed of light, our mass will become infinite. The faster you go, the heavier you become. We don't feel relativistic mass change when in the normal sense, is because our mass is pretty small and the speed with which we are going is laughably low. Okay, but if we try to move at the speed of light or near the speed of light, our mass would gain. So basically energy is getting converted into mass. You know, E is equal to mc square, right? Einstein famously said that mass and energy are interconvertible, right? So basically if you're trying to move really really fast, the energy that you have will slowly and slowly get converted into mass. More mass, more mass, more mass. Eventually you will have infinite mass when you're traveling at the speed of light. That is the reason, that is the physical barrier that we have, for which we cannot move at the speed of light. Okay, in the future physics might change, but for now that is the answer for us. Okay, this is a very large speed. Did you understand this question? Any doubts in this question? Any doubts? If you have any doubts, this is the time to ask. Okay, next. Yeah, because this is in mega electron volts. Electron volts has to be converted into joules if you want to find the speed in meters per second. Clear? So speed, that is the requirement. Okay, that is a requirement that you need to understand. Okay, let's move on. Now, tool number one. Recognize and, oh, what is this? I'm gonna. Shall we skip this? Okay. A lot of experiments. Now, the next topic that we are going to learn is the field lines close to a conductor. I have already told you that the electric field lines enter a conductor perpendicular to the surface, right? The electric field lines enter a conductor perpendicular to the surface. One second. So, the field close to a conductor. The charge Q stored on the parallel plates in the two parallel arrangement depends on the potential difference V between the plates, the area of the plates and the separation. Okay, so the charge, how much charge can be stored depends on the potential, the area, and it is inversely proportional to the distance between them. Okay, so let's see. These relationships can be combined to give Q is directly proportional to VA upon D, where the constant of proportionality turns out to be 1 upon 4 pi K, and therefore Q is equal to VA upon 4 pi KD. Okay, so this expression can give a value for the density of charge on a surface, density of charge on the surface of the charged parallel plate. It can be rearranged as Q upon A is equal to 1 upon 4 pi epsilon, sorry, 4 pi K 4 pi k multiplied by V upon D. Here, Q upon A is the charge per unit area, the surface charge density sigma. So, we use the term sigma to represent the surface charge density. The unit of sigma is what? Coulomb upon meter square, Coulomb per meter square, Cm to the power minus 2. Therefore, between two parallel plates, E is equal to 4 pi k sigma, the electric field. Understood? 4 pi k sigma. Okay, now where does this 4 pi k sigma come from? 4 pi k into sigma is what? Charge upon area. Uh, yeah, basically. Okay, look at this. So sigma is equal to Q upon A is equal to 1 upon 4 pi k multiplied by your V upon D. So V upon D is what? V upon D is the electric field. So sigma is equal to 1 upon 4 pi k times electric field. So electric field becomes equal to 4 pi k sigma. Understood? This is how you get this formula. Each plate contributes half of the field, so that the electric field very close to the surface of any single conductor is equal to this whole value upon 2. You will get E is equal to 2 pi k sigma. Very close means close enough for the surface to be considered locally flat. Understood? You are going very close to the surface. So very close to the surface, the electric field becomes equal to 2 pi k sigma. At the center, it becomes equal to 4 pi k sigma. Okay. Now, perpendicular to the surface. Okay, perpendicular to this is the diagram for perpendicular to the surface. Parallel to the surfaces, what happens? The forces cancel each other out, leaving electric field only perpendicular to the surface. Understood? When you are talking about the horizontal field lines, they are moving away from each other, right? Like they are moving away from each other and in the opposite direction. So what happens? The field produced by this gets cancelled out by the field produced by this. Therefore, what ends up happening? Only the perpendicular component of the field lines actually matters. Okay, so that is the reason why we say the electric field lines always enter perpendicular to the surface, because the component, the x component or the parallel component of the surface of the electric field, because of their direction, because of their orientation to be in the opposite directions, what happens? The electric field cancels each other out and you end up with only perpendicular field lines leaving the surface. Understood? Or entering the surface. So an electric field line, if it has to leave a conductor, it can only leave perpendicularly. Understood? Horizontal component cancels each other out. Okay, So, although from a distance away the surface of a sphere is curved, very close to the surface it appears flat, and the electric field lines are locally normal to the surface. The electric field lines are always locally normal to the surface. Understood this logic? Okay, let's move on. Okay, imagine going very close to the surface of a conductor. Figure 19 shows Figure 19 shows what you might see in the case of a conducting sphere. When we are sufficiently close to the when we are sufficiently close, the surface appears flat, just as we are not aware of the Earth's curvature until we see it from space. That was one of the major reasons why people thought the Earth was flat, because the Earth appeared flat because of the fact that Earth is massive. Okay, Earth is massive, so you can consider the surface of the Earth at any particular point small enough to be a flat surface. Okay, so we would also see that free electrons are equally spaced. This is because any electron has forces acting on it from all the other electrons. The electrons will accelerate until these forces balance each other out and it's in equilibrium. For this to happen, they must be equally spaced. The electrons on the surface must be equally spaced. Understood? So, like basically, this is a little bit like an imaginative part only. You don't have to know it by heart. The electric field vector radiate out from each individual electron. Okay, acting on a point source. Parallel to the surface, all the vectors cancel each other out. So there is no electric field along the surface like this. There is no electric field. If there is an electron here and an electron here, both of them will be producing electric field both perpendicularly and horizontally, right? Both of them will be producing fields perpendicularly and horizontally. Actually, they are not. They are producing a field at a certain direction, but we have resolved that electric field into the horizontal and the vertical component. So the vertical component remains, the horizontal component basically cancels each other out. The horizontal component cancels each other out. So no electrons accelerate along the surface because the component of electric field strength is zero. There is no horizontal component of electric field on the surface of the conductor. So the electrons do not accelerate. They only move with a constant velocity. Perpendicular to the surface, however, things are different. The field vectors add up, right? All these all these vectors are parallel to each other, right? Every single vector is parallel, like in this diagram. So what ends up happening? All these field lines will add up. They are in the same direction. They will add up. Okay, they will add up. The field vectors add up because there is no field component parallel to the surface. The local field must act 90 degrees to the surface. Close to any conducting surface, the electric field is at a 90 degrees to the surface and has a strength of E is equal to 2 pi k epsilon naught. So even if you have a curved surface like this, an electric field is coming like this, the electric field will always enter the surface like this. Okay, it will always enter perpendicular to it. Understood? It will always end up perpendicular because again the horizontal component gets cancelled out. So there is no field in the horizontal component. There is no acceleration in the horizontal component, and therefore only the perpendicular region remains. Only the perpendicular region allows the electric field to enter through. Clear? Okay. Fields due to conducting spherical bodies. A. Outside the sphere. Knowledge of the electric field very close to a conductor can be taken a step further for a conducting sphere, whether hollow or solid. Okay, what is a hollow sphere? A sphere that is only a shell is called a hollow sphere. Understood? There is emptiness inside. Again, the free electrons on the surface are equally spaced. They are all equally spaced from each other, and the field lines at the surface of the sphere are 90 degrees to each other. The consequence is that the field must be radial, just like the field of an isolated point charge. To a test charge outside the sphere, the field of the sphere appears the same as that of a point charge. Mathematically, mathematical analysis confirms that outside a sphere, the field indeed behaves as though it is coming from a point charge. So basically, if you have a sphere like this, since all the field lines are perpendicular to each other, perpendicular to the surface, we can assume that all these field lines are originating from the center of the sphere. Okay, my drawing is a little bit crass, but at least you can see it. Okay, one second, hold on. Okay. Mm, so because the surface of the sphere is always perpendicular to the electric field, we can assume that all these electric field lines coming from an imaginary charge that can be placed at a center point. That means basically you can assume the sphere to be a point charge of having a certain charge. Okay, whatever charge may be spread across the surface of the sphere can be considered to be concentrated at a small point at the center of the circle. Okay, this is what they're trying to say. Okay, now inside the sphere, things change. Inside the sphere is a different matter. There is no electric field inside a conducting sphere, conducting hollow sphere or a solid. As a result, this was experimentally determined by Benjamin Franklin. Hollow or solid? A result that was experimentally conducted by Benjamin Franklin. It can be shown using Coulomb's law and the idea of surface charge density. Because the sphere is a conductor, all the surplus charge must reside on the outside of the sphere. This follows because the charge will not move until they are as far away as possible. Okay, all the free charge that is present on that hollow sphere must reside on that surface, not inside the surface, because they want to be as far away from each other as possible. Okay, and to be as far away from each other as possible, your distance, your surface, you have to spread across the surface, top of the surface. Basically you have to arrange yourself on the surface of the conducting sphere. Okay, they are all in equilibrium, which as earlier means that they must be equidistant on the surface. To find the field strength inside the conductor, we need to compute the force that acts on a positive test charge q placed at a random position inside the conductor. Okay, for example, you have a conducting sphere like this, and this is a random point. This is a random point or where you have placed a small test charge q. Okay, this is a random point where you have placed a small test charge q. Figure 20. Where is figure 20? Is it in this page or the next page? No, it has to. Okay, fine. This is a random point on the sphere. Okay, let's understand what is happening. What is the force acting on this test charge? Focus on the two cones that meet at the test charge. These are the two cones. Okay, this is a cone, and this is another cone that you are having. Clear? Okay. So focus on the two cones that meet at the test charge. The test charge is close to the conducting surface on one side, so one of these cones is small and the other is large. The surface charge density on the cone is sigma over the whole sphere. Analysis shows that the force acting on the test charge due to these two surfaces are equal and in opposite direction. Understood? So basically, what is happening? One cone having a larger surface area basically is attracting the charge that test charge with the same force with which that small charge is doing. Okay, now How do you analyze this? Okay, now how do you analyze this? So this this part of the sphere has a larger number of charges. So this part of the sphere will have a larger charge magnitude. So this part will have a smaller charge magnitude. But we know that force is directly proportional to the charge and inversely proportional to the distance. What is happening here? Even though you have a large amount of charge, you are far away. But here you have less amount of charge and you are close by. So what happens? Both of these try to repel the charge particle. This is a positive charge. This is also trying to repel it. This is also trying to repel it. Okay. Now what happens when you have two forces acting on you with equal magnitude in opposite directions? They will cancel each other out. So there will be no net force acting on the charged particle. If the net force acting on a charged particle is zero, then electric field is equal to force upon charge. Zero upon charge also becomes zero. Understood? So this is how this happens. So even though there is more charge concentration here compared to here, you are having basically the same force because of the distance. Understood? So at the center, it will be more obvious. At the center, both the distances will be the same. Both the area of the cones will be both the bottom areas of the cones will be the same. There will be the same amount of charges present here and here when the particle is at the center. So what will happen? At the center also, the forces will be of the same magnitude in the opposite direction. So they will cancel each other out. They will cancel each other out. Understood? Okay. Now, inside the sphere, the electric field is zero. Outside the sphere can be assumed to be a point charge. Outside the sphere can be assumed to be a point charge because the field lines are perpendicular to the sphere. But inside the sphere, what happens? Inside the sphere, there is no electric field. Now, if there is no electric field, then there is no force. If there is no force, then moving a charge from one point to another will not require any work. Zero work will be there, right? If the work done is zero, yeah, exactly. So we are going to connect all the dots slowly and slowly. We are going to connect all the dots. Okay. Analysis shows that force acting on the test charge due to the two spheres are equal and opposite in direction. The forces cancel each other out, leaving no net force due to these two areas of charges. This proof applies for a pair of cones or and any test point inside a sphere. There is no net force on the test charge anywhere inside the sphere. Consequently, there will be no electric field. If there is no force, if there is no net force, there is a force, but there is no net force. Because there is no net force, there is no electric field. Okay? Okay, let's actually read this. Benjamin Franklin was a scientist who conducted research into electricity and electric fields. He was the first to use some of the languages and vocabularies still used to describe electricity. Examples such as charging and discharging and the distinction between conductors and insulators came from Franklin. Okay, so and the distinction between conductors and insulators came from Franklin. He famously flew a kite during a storm to demonstrate that lightning was an electrical effect, and he invented the lightning rod. Okay, and that has saved a large number of people. Okay, because instead of the lightning falling on the house of people, it falls on the rod, and the rod conducts it straight to the earth. Okay, so he was the inventor of the lightning rod too. Franklin was also a writer, printer, and a publisher. As a politician, he was one of the founding fathers of the United States and one of the drafters of the Declaration of Independence. In his autobiography, Franklin devoted a significant portion to self management. He identified 13 virtues: temperature, silence, order, resolution, frugality, industry, sincerity, justice, moderation, cleanliness, tranquility, chastity, and humility, and reflected at the end of each day upon whether he had fallen short in any of these virtues. He concentrated on one virtue each week to practice and strengthen that virtue. He also constructed an order so that every part of his business should have its allotted time. Franklin acknowledged that other people might have their own routines and that when his business involved other people, the compromise would be needed. Oh, that's actually a good thing. When you are running a business, you should not run with the comfort of your own. You should basically try to work with the comfort of the people you are trying to serve. Well, that's actually a good thing. Okay, very good. Now, Millikan's experiment to determine the charge of an electron. Okay, this is the famous oil drop experiment. Okay, now J.J. Thomson was the one who basically found the charge to mass ratio of an electron. Millikan, with his oil drop experiment, was the one to actually determine how much charge there is in one electron. Okay, in 1909, the American physicist Robert A. Millikan and Harvey Fletcher carried out an elegant experiment to estimate the charge of an electron. Nowadays, the experiment is attributed to Millikan alone and is known as the Millikan's method of determination of an electron's charge. Millikan won the Nobel Prize in 1923 for the contribution of his work on this and the photoelectric effect. Okay, we will learn more about photoelectric effect in later chapters. But for now, we are just going to figure out how he discovered the charge of an electron. The method has two steps. A cloud of small oil drops is sprayed into a chamber. Okay, it's called a vaporizer. Okay, a vaporizer. What is a vaporizer? What does a vaporizer do? It converts the liquid into small vapors. This is what happens every time you spray perfume. The liquid inside the perfume becomes vapors, very, very small droplets of the liquid. So he used a vaporizer. Okay, these drops are ionized using the X-rays as a source of beta particles, or they charge by friction as they fall through the aperture into the chamber. One drop is selected and allowed to fall through air in the absence of an electric field. The drag force, together with the buoyancy force and the gravitational field, lead to zero resultant force on the drop during the fall. Measurement of the terminal speed of the drop allows the weight of the drop to be calculated. Okay, so what is happening without the field? Basically, he is dropping an oil drop. He's basically allowing the oil to drop. Okay, and there he is figuring out the viscosity, the terminal velocity, and all the resultant forces acting on the droplet. Okay, he is trying to figure out the amount of force that is acting on the droplet. Step 2, the same drop is charged while the apparatus while in the apparatus and is held stationary using an upward electric force. Now imagine this. Okay, there is a charged particle going down, a positively charged particle going down, and you are trying to balance it out with the help of an electric field that is going upwards. Okay, you are balancing it out with an electric field that is going, no, basically the negative plate was downwards, the positive plate was upwards. So basically when the electron was going from here to here. Okay, one second. Yeah. Oh, what is happening today? So the same drop is charged while in the apparatus and is held stationary using an upward electric force that is equal and opposite to the weight. This allows the electric force on the drop to be determined. Okay, so basically he balanced the force of gravity of that droplet with the electric force of the plates. Okay, and when he balanced them out, the two sets of experiments allows the excess charge on the drop to be estimated. He found the force on the droplet using the this thing, electric force method, k q1 q2 upon r square. Okay, he found the force, he found the Akshay, he found the force. Okay, he wanted to know what the charge would be. Okay, so basically if it is floating in the air, then the force applied by the electric field would be equal to the force of the gravitational field if it is just floating in the air, right? If it is simply floating in the air, gravity is pulling it downwards. The electric field is providing a force on that electron to move upwards. Both of them are balancing each other out. So you get what? You get a floating oil droplet. Okay, now the two sets of measurements allowed the excess charge on the drop to be estimated. Millikan and his co-workers found that the excess charge was always an integral multiple of the basic charge. Okay, they always found that it is either 10 into 10 raised 1.6 into 10 raised power minus 19 coulombs, or 20 into 1.6 into 10 raised power minus 19 coulombs, always an integral multiple of some value, some value. And that value was, when they figured out what the value was, they gave it they said that this value is equal to the charge of the electron. Okay, so he ascribed the basic charge to the charge of one electron. When many drops have been measured, each with many different charges, it is possible to estimate the lowest common denominator of all the charges. To see how this works, imagine that you have several opaque bags containing identical objects. You know that the, one second. So, uh, to see how this works, imagine that you have several opaque bags containing identical objects. You know that the mass of each bag is negligible. Can you estimate the mass of one object? Suppose the masses of four bags are 420, 840, 560, and 1260. The highest common factor of these measurements is 140 grams, indicating that this is a good estimate for the mass of one object. If you have multiple objects in each bag, okay, if you have like 10 apples in one bag, 20 apples in the other bag, 30 apples in the other bag, and if you try to calculate the highest common factor in all of them, what will happen? When you try to calculate the highest common factor in all of them, you will able to calculate the mass of one apple. One single apple's mass can be calculated because all of them will have that one factor. One highest common factor will be there, right? So there will be like 3, 6, 4, 9 objects respectively in the bag. However, if the mass has been 420, 840, 630, and 1260, then the highest common factor is now 70, and you will need to revise the object's mass down. This was the basis of Millikan's method. After many trials, he estimated the elementary charge to be 1.592 plus minus 0.003 into 10 to the power minus 19 coulombs. Later, experiments have failed to find a lower value of this charge, even though the value for E has increased slightly over 100 years since the original experiment. Nowadays, the electronic charge is a matter of definition, and the value assigned to E is 1.6 into 10 raised to minus 19 coulombs. This thing does not change. So Millikan was able to figure out the charge of an electron by conducting various experiments. He did this experiment again and again and again, and every time he figured out there was some factor that was common. The lowest value that was possible was calculated by Millikan, and like basically when the technology improved, they figured out that he was slightly wrong, right, by a factor of 0.0 something something something. So basically, now the exact value is 1.6 into 10 to the minus 19 coulombs. Understood? Okay, this is the Millikan's oil drop experiment. Now, Millikan's work shows the importance of error estimation in scientific experiments. He claimed an error of about 0.5% at the time. However, later experiments of the original notebook showed that of the 175 drops that he measured, only 58 were used for the final result of E. There are comments in the notebook about the 100 or so drops that were ignored. These range. these range from this is almost exactly right, though error high not used, to too high by 1.5%. Experiments that collected data and are sampling random points on a natural distribution. Okay, he is just telling us how he did it. Okay, basically, this is nothing but the ways he used to calculate the value of charge. Okay, so I think this is the next topic is going to start, right? Can we do one thing? Can we start the next topic tomorrow? Understood? Okay, so we will start the calculations. We'll probably be able to finish this chapter by like 2 or 3 more classes. Understood? I don't want to rush into this. We will complete this chapter eventually, like two or three classes maximum it will take. Okay, so the class has ended now. I hope you liked my video, and if you like the way I teach, please do like, share, and subscribe to my channel. And I'll meet in the next video. Thank you.